Welcome once again. We are still in the business of making things very easy for you in your studies. And so when it comes to LearnRite, we don't just say the things, the facts. We illustrate with demonstrations and practicals. Today we are going to look at the fifth point of interest, which is the physical properties of ionic compounds. We are looking at the physical properties of ionic compounds. Remember, we stated 5 things that we are interested in: the nature and the formation, units of current lattice size, intermolecular forces, and then examples and how the formulas are written. And the last point is the physical properties of ionic compounds. Now, electrostatic force of attraction are quite strong, and it doesn't occur only within the molecule or 1 mole of the ionic compound. It's the same force, the electrostatic force of attraction, that exists between molecules of the ionic compounds. So whether beside, within, or wherever, it is electrostatic force of attraction. So because of this, all ionic compounds are solids at room temperature. In fact, they are crystalline. Examples, like this salt, it's quite hard. I cannot easily break it on my fingertips. No, I'll hurt myself. That is potassium nitrate, the saltpeter. Count that you know in your kitchen too. That is also very hard. I cannot easily break it, okay? They are solids at room temperature. But of course, we can describe the strength of ionic compounds. Some ionic compounds are more stronger than others, depending on the charges on the ions. +2 - 2 or +2 - 1 time with 2 of the molecules existing will be stronger than, it will be stronger than a +1 and -1. Okay? In other words, group 2, to me, group 2 group 2 elements, when they form ionic compound, because they would have given out 2 electrons, and these 2 electrons would have been accepted by the non-metals, they will form stronger forces than +1 metals, that is than the group 1 metals. So these are examples of solids that are ionic compounds. The normal salt, sodium chloride, we see it in our kitchen. The saltpeter, potassium nitrate, okay, which is of course also the kind that you know in your kitchen. They are all solids at room temperature. And when we ask you why, you say because of the forces of attraction within and between are all strong electrostatic force of attraction. Now, because they are ionic in nature, or they are polar in nature, they also dissolve in water. They dissolve in water. Almost all ionic compounds dissolve in water, irrespective of how long it takes to dissolve in water. Why? Because ionic compounds are polar and water is also polar. We say like poles attract each other. They will say like poles repel each other and opposite poles attract each other. But when it comes to solubility, here we want polarity to occur between the solute and the solvent molecules. If they are both polar, they interact with each other through what we call the dipole-dipole interaction. And because of that interaction, the forces, the electrostatic forces that hold the ionic compounds together are broken, and the ions will become separated. They move about in the solvent. Here, I'm saying they are soluble in water because water is a polar solvent. And the ionic compounds are also polar in the sense that they have the negative and the positive poles. So as soon as you dissolve any salt, we dissolve salt in water. You all know it. You have been doing it. And also the saltpeter. Remember, when you are doing your soup and you put the can in it, it dissolves. Okay. So if I put this one in water and I stir it, within a short time, you see that all the salt will dissolve. Why is the salt dissolving in the water? In chemistry, dissolution occurs when solute particles are able to interact with solvent particles. And this only happens because they are all polar. The interaction between them will be dipole-dipole interaction. And when this interaction occurs, the solute particles are broken apart and they dissolve in the solvent particles. Now, this salt will not dissolve in nonpolar solvent. Petrol is dangerous to me, so I didn't bring petrol here. But at least I have fritol, which is also a liquid, a nonpolar substance. It is oil, an organic compound. I'll pour some and try to dissolve the salt in it and see whether it will dissolve or not. We can leave this salt in this oil, which is also a solvent, till tomorrow, or the kingdom come. It will not dissolve it. I know you are thinking in your mind that but say when we are cooking, maybe with oil, you put salt in it and it dissolves. Yes, water would have been in the stew or somewhere, and it's because of that water particles there that let the salt dissolve. But with only oil like this, you stir and stir and stir and stir, it will not dissolve. If you can see, the salt particles are still in there. Because the oil that you see, which is fritol, is an organic compound which is nonpolar. If it is nonpolar, the salt are put in there which is polar can never interact with the oil particles in any way. So none of the electrostatic forces or the bonds in the solid, which is the salt, will be broken. And so dissolution will not occur, or solubility will not occur. That is one physical property of ionic compounds. They are solid. Number one, they are solid at room temperature because they have the strong electrostatic force of attraction, both within and between molecules. Number two, they are soluble in polar solvents because they are also polar solutes or polar solids. So together in the polar solvent, they interact through dipo-dipo interaction, and this interaction leads to a breaking of the bonds or forces in the solute particles, so they dissolve. In nonpolar solvents, the ionic compounds will not dissolve because the nonpolar solvents, like oil that we are seeing, the nonpolar solvents are nonpolar, so they don't interact with the solute particles in any way. And before solubility can occur, the interaction will bring about a certain energy called solvation energy. Solubility occurs only when solvation energy is higher than the forces of attraction between the solute particles. When solute particles interact with solvent particles, if there's any interaction at all, the interaction leads or brings about what we call a solvation energy. But if the solvent in particular is water, that solvation energy is specifically called hydration energy. Okay? So solvation energy and hydration energy are more or less the same, except that solvation energy is general for all solvents, whereas hydration energy is specific to water. So you'll not be wrong to say that solvation energy generated in a certain solute and water. You'll not be wrong. But specifically, if you want to be more correct, you can say that hydration energy. So solubility occurs only when solvation energy created out of the interaction between the solute and the solvent particles becomes so high that it breaks the forces holding the solute particles together. But where I have this salt and the oil, see, they are still there. The oil is nonpolar, the salt is polar. There is no interaction between these two particles. So solvation energy created is virtually nil. And once it is nil, then the forces of attraction between the solid particles, in this case, electrostatic forces, are still holding the particles together. That is why it doesn't dissolve. So the whole concept about solubility, which we will treat again when we come to treating solubility as a topic, is that put a solute in a solvent. The solvent should be able to interact with the solid particles by some means. It could be dipole-dipole interaction, it could be hydrogen bonding or covalent or whatever. If they are able to do that interaction, then a solvation energy is created, which, if it is high enough, will break the intermolecular forces of the solid before the solid will dissolve in the solvent. But here, if you are using water, we are saying the solvation energy is specifically called hydration energy. So here, the salt in the oil, we are expecting an interaction to occur. The oil is nonpolar, the salt is polar, no interaction is occurring. One may not be able to say whether solvation energy is created at all or not. Even if it is created, it is not enough. It is so small that it's not able to overcome the attraction between the solid particles. And so dissolution doesn't occur. That is what we mean by polar dissolves in polar solvent, but polar solid that do not dissolve in nonpolar solvent. But nonpolar may also dissolve in nonpolar, because over there they will attract each other through van der Waals forces, or they will interact with each other through van der Waals forces. Okay? Yes. So that is the explanation. So I have discussed 3 points. The point number 4. Ionic compounds have high melting points and boiling points. Why? Because of the strong electrostatic force of attraction within and between the molecules of ionic compounds. The ionic forces or the electrostatic forces are strong. So if you want to melt it, you need to apply more energy. So to have a higher melting or boiling point than other compounds that will have weaker bonds between them. That is it. Now, the next point, which is very, very important, is that ionic solids in the solid form do not conduct electricity. Why? Because in the solid form, the ions, though are in the solid, they are held together by the electrostatic force of attraction, as we saw in the video, in one of our videos. The electrostatic forces are held together, so the ions are not free to move. Electrical conductivity is due to either movement of electrons or movement of ions. In other words, electrical conductivity is mainly due to movement of charges. And charges, we know, can either be positive or negative charges, or the negative charges can be due to electrons, movement of electrons. So in ionic compounds, in the solid form, there is immobility of ions because they are held together by the electrostatic forces. So they cannot conduct electricity. Let me show you this. I have this battery giving me some current. And so we have not done metallic bonding yet, but metals conduct electricity. If I put this together, do you see the light coming? Here, I want you to watch here. If I put the wires together, I have light, okay? Let me put it in this solid sodium chloride. Do I see any light coming? It is telling me that the solid sodium chloride is not conducting electricity. Let me put it in the saltpeter, potassium nitrate. Do I have any light coming? No. Let me do some experiments. First, with distilled water. Distilled water means that any ions in the water has been taken off. It's simply, in chemistry, we call it deionized water. It means there are no ions in it. I'm pouring this pure water. You call it pure water, but that is deionized water. But of course, most of our pure water sold on this are not deionized. They will have ions in them. This one is specifically taken from a lab. Deionized water. In your lab, you see there, it's called distilled water. Because if you don't use distilled water to do experiments and use ordinary water, which has ions in it, it will interfere with your results all the time. That is why most often we use distilled water in our laboratories in doing our experiment. So this is distilled water. I'll put the negative ends. Do you see the light coming? I don't think so, because it is deionized. No ions existing in this water. I'm pouring this one away, and I'm going to fetch ordinary water. Ordinary water has some ions in there. Why? You grow to know it. But let me tell you today that we use chlorine or chloride to treat the water that we pump from rivers, because they may have some germs and other things. So when you treat it, the ions stay in the water. So this water flowing here is ordinary water coming from Ghana Water Company. They have treated the water. As you are drinking it or as you use it, you have some chloride ions in it. And once it is there, ions, because you use that compound, the chemical compound, sodium chloride or something to treat the water, the ions are existing in that water. the ions in that water has not been removed. So we call it ordinary water. Any water named as ordinary water treated from waterworks will have some chloride or will have some ions. So let's see whether ordinary water conduct electricity or not. And why we say water is polar. If we say water is polar, it means that it has some positive end and negative end. And once you have positive end and negative end, then electrons coming from these electrical systems here will go through the positive end, and then electrons will flow through it, and therefore it should be able to conduct electricity. So this is ordinary water, which I suspect will have ions because of the way the water was formed. Let's see. Is the light coming? It is coming, isn't it? I cannot see it from here, but I believe my science. Yes. That is the light. But do you see that it is a bit dim? Why? Because it doesn't contain much ions. Ordinary water is not as polar as ionic compounds. Ordinary water doesn't contain as much ions as ionic compounds. So I've demonstrated that water ordinarily contains ions, and so we say water is a polar molecule. That's why we said ionic compounds will dissolve in it, because it's polar, so they will interact. Okay, but if you have deionized water, all the ions have been removed from it, and so it will not conduct electricity. Now, I'm going to change this. I've shown that ordinary water conducts electricity. Now I'm pouring this one away, and I'll dissolve. Okay, let me even use this water. And let me use this so that you know that ordinarily this one has no ions. Then I'll dissolve salt in it. Now, if I dissolve this salt in the water, what am I doing? I told you that once the salt is polar and the water is also polar, and I'm dissolving it in it, if I get the salt dissolved, I have broken all the ions, that is the sodium ion and the chlorine ion, from each other. The rheostat forces of attraction are no more holding each other very strongly. So the ions in there are able to move. If the ions are able to move, then they should conduct electricity. Like I said, electricity is basically due to movement of ions or electrons. Okay, so now I might dissolve sodium chloride here. Let's see whether it will conduct electricity. Have you seen that it has come? Science is truthful, just like God. Science is all about studying God. So we understand God, and then we come out to understand the world better and make life very easy. So look at it. It is conducting electricity. Separated. I'm not joining the metals together. But ordinarily, the distilled water did not conduct electricity. The ordinary water conducted electricity, but it wasn't as high as the ions here. Now, because I've dissolved the sodium chloride, which is an ionic compound, in the water, the ions in there are more, and the movements are very high. And so that is why it is conducting electricity more. So, very often you get this question. Solid sodium chloride or solid lithium fluoride or solid potassium chloride does not conduct electricity, but molten sodium chloride or potassium chloride does. Explain. Then you say solid, the answer will be that solid sodium chloride does not have ions in it to conduct electricity. The ions, sodium plus and chlorine minus, are held together strongly by the electrostatic force of attraction within and between them. So the ions are immobile. However, molten sodium chloride, molten, let me write it on the board, simply means liquefied or dissolved, okay? The other say dissolved or molten sodium chloride. That is a solution of sodium chloride. A solution of sodium chloride conducts electricity because the electrostatic force of attraction between the ions have been broken. The ions are now free to move in the system. And once they move in the system, then the ions will help. You see, when this electrical conductivity is when for metals, when I put them together, they are joining each other straight away. When I separate them, it goes off. There is no substance to continue with the electron flow or the mobile flow. So why is that when I put it in that solution, still the metal is not connected, it is giving me light. It's giving me light because the circuit is completed. The flow of the electrons through the water is completed. And that is why if you have an electrical system that is perforated in the bathroom and it's touching the water, and you go and bath and you don't know, you die. In politics, very recently, the follower of the current vice president, Dr. Baumia, if you saw the story, they went somewhere in a hotel, the bathroom, the electrical system was faulty, and so he went into the bathroom, and because there was a wire touching the bath, conducted through there, after pouring water himself and the wire was dropped in there, it killed him instantly. Why? Because electrons or ions moved through him because of the water that was on his body, and he died. I wonder if he knew about what we are doing. If he knew and he stepped in and saw that there was that electron flow through him, quickly he should have moved away from the water. Quickly. It will hurt you though, but he would have died. But I'm sure he poured the water too much of it. No one can explain. But when they went to find out, of course they saw that a naked wire was somewhere in the bath. That is what killed him. Very unfortunate though. Very, very unfortunate though. But that is something you as a science student should know and be telling your colleagues who are not science students all the time. So these are the 4 or 5 physical properties of ionic compounds. I repeat them. They are solid, they are crystalline solids at room temperature. The reason being that the electrostatic force of attraction, which is strong, exists both within and between the molecules. They have high melting point and boiling point for the same reason, because the intermolecular forces and the intramolecular forces are strong because they are electrostatic force of attraction. They are soluble in water and other polar solvents because they are polar. So when you drop ionic compounds in such polar solvents, they interact with the solvent molecules through what we call a dipole-dipole interaction, and the solvation energy or the hydration energy generated is enough to break the intermolecular forces of the ionic compounds, so they dissolve. However, in non-polar solvents, they don't dissolve because they don't interact with the non-polar solvents in any way. Solvation energy, if generated at all, is so small that it doesn't overcome the intermolecular forces, so the ionic compounds will not dissolve. Lastly, ionic compounds do not conduct electricity in the solid state because the ions are held together and the ions are not able to move. But in the molten state or in the liquid state, when they are dissolved, the ions are broken apart, they are separated from each other, and the ions move in the system, and this allows electricity to flow through. So these are the physical properties of ionic compounds. If you are asked to list 2, 3, 4, 5 with reasons, you have to list them. But if you are asked to list them, just go ahead, look at the question. Well, when we finish the totality of bonding, we'll look at questions. But normally, questions that will come on the physical properties are some of those that I've asked. Explain why they'll mention the ionic compound. Conduct electricity in molten state, but not in the solid state. Why does maybe lithium fluoride has a high melting point? All this. They'll ask questions on this. Sometimes they'll just ask you, list 2 or 3 physical properties of ionic compounds, and you have to just list them. They don't ask you to list with explanation, just list. They conduct electricity in the molten state. They are solids at room temperature. They are this. But if you say with reasons, they must go ahead and state the reasons. Is chemistry difficult? I don't think so. Even if it was to you, with LearnRite, you see how we are breaking it down. It is a fun game, very interesting. We will continue to make chemistry very, very attractive to you. so that you grow to like chemistry, and for that matter, the totality of science. I'm not done yet, but more or less, this is the end of ionic compounds. We are going to continue in our next video with metallic bonding. Come with me, don't stay away. Metallic bonding in our next video. Thanks.